Now let's look at at a phenomenon called aliasing. It's when we actually, it occurs when we don't meet the Nyquist criteria, or we sample at a rate less than twice the highest frequency in the signal. So I'm going to use a different baseband or low frequency spectrum to illustrate what happens here. So here's the Fourier transform of my continuous time signal. Say it looks like this, and it has the highest frequency in hertz of B, or in radians per second, 2 pi times B. And again, I'll give it an amplitude A here. We know what the spectrum of the ideally sampled signal looks like. And if we actually meet the Nyquist criteria, so we'll have replicas of this at omega s apart. And as I've drawn this is 2 pi b, I'll have a gap between this baseband replica and the replica that's at omega s, as long as omega s is greater than 2 times 2 pi b, or equivalently in hertz, f of s is greater than 2 times b, which again is the Nyquist criteria. And I'll be able to then recover, this would actually have a height of a over t. I can actually then go from x over bar of omega back to x of omega by low pass filtering x of omega. Okay. Now let's look at what happens as I reduce the sampling frequency here. I'll draw an intermediate picture where I just meet the sampling criteria. So I've got this, and then now these things are just bumping. I've reduced omega s so that these things are just bumping into each other, just adjacent. So this is 2 pi b. This is minus omega s. Okay. And so in this picture, I've set my sampling frequency, so it's just equal to 2 times 2 pi b, and then so all of these replicas are just touching one another at this frequency of omega s over 2, since omega s is equal to twice 2 pi b. I can still recover the original x of t, again by low pass filtering. I'd low pass filter using a filter with a bandwidth of omega s over 2. Okay. And then I want to draw one more picture. For the case where omega s is actually less than 2 pi b. And so now I'm violating the Nyquist criteria. I'm going to draw in the individual spectrum as just dashed lines here first. Show the baseband spectrum, and then the one that's just adjacent to it. Okay, so this is omega s. And then again, the next one would look like this, and then the one down at minus omega s would look like this. This frequency is omega s over 2. Now, the actual spectra, if you recall, is our formula for the spectrum is the sum of these shifted, it's actually a 1 over t factor, the sum of these shifted baseband spectrum. I've drawn the individual shifted versions. What I actually see is the sum of all of these. Now there's an interval here where I'm just seeing a portion of one spectrum, and so in that case, in the sum, that's the only term that would contribute. But there's a region here around omega s over 2 where I have to sum two adjacent replicas. Okay. So the sum of all of these is going to look something like this. Again, this continues out to infinity in both directions. Okay. Point is now that if I low pass filter with a filter that has a bandwidth at omega s over 2, okay, essentially this frequency minus omega s over 2, I'm not going to get back the original spectrum. I'm going to actually recover a distorted version of the spectrum. So low pass filtering would give, I'll call this x with an overbar of omega, because it's not really, I'm sorry, with a tilde, because it's an approximation to x of omega. So again, this is a baseband spectrum, but it's not the spectrum that we actually had originally. It's going to look, something like this for the figures I had on the previous page, okay, where this is omega s over 2. And then, what's happening here is I'm losing these frequencies that are above omega s over 2, and then some frequencies that are below omega s over 2. I'm getting distortion there, not the original spectrum, because of the adjacent replica. Those frequencies above omega s over 2 are actually, the term that's used is they're said to be folding back and causing then distortion in frequencies below omega s over 2. So this undersampling, the term that's used is aliasing. It actually causes distortion in two ways. Frequencies above omega s over 2 are lost after low pass filtering. They're chopped off in an attempt to recover the original signal. And then the other effect is that there's distortion in frequencies below omega s over 2 due to the presence of frequencies that are actually above omega s over 2. Okay. We can actually eliminate the second type of distortion if we use a low pass filter before we sample. So low pass filter, the bandwidth of this filter needs to be omega s over 2 or fs over 2 in hertz, and this is called an anti-alias filter. We're still going to lose any frequencies above omega s over 2. They're now going to be lost by low pass filtering, but at least they're not going to be causing additional distortion. And so this would occur before sampling. And if you recall, we sample by just multiplying our signal by this impulse train to get our sampled version of x of t. So before you do sampling, the point here is that before you sample, you should always use an anti-alias filter to eliminate any frequencies that are above the Nyquist frequency divided by 2. This will help to minimize the distortion that's caused by aliasing.